Hello everyone, I'm Tony from Intel. Today I will give a talk on fault-aware prediction-guided page offlining for uncorrectable memory error prevention. This is the joint work with Xiaoming Du and Shenzhou from Intel, and Xian Liu, Xiaohan Xu, Tianjiao Wang, and Shi Jienge from ByteDance. Here is the outline of my talk. First, we will briefly introduce the background of DRAM errors and page offlining. Next, we will describe the weaknesses in traditional methods and evaluation. After that, we will propose our new approach, fault-aware prediction-guided page offlining. We then demonstrate that the new approach is much better through empirical evaluation. Finally, we will give the concluding remarks. A DIMM composes of a few DRAM chips. Each chip contains a number of banks, and each bank is a two-dimensional array, indexed by rows and columns. When memory gets accessed, each chip provides part of the content of a cache line. When part of the DIMM is faulty, a read operation over the faulty location may result in a cache line with some error bits. Note that even if the fault is permanent, the error bits can be uncertain. Error correction code is applied. If the error bits are within the ECC's capability, it becomes a correctable error. If they go beyond the ECC's capability, it becomes an uncorrectable error, typically leading to a system crash. From OS view, memory are organized as 4 KB pages. A physical page is interleaved over multiple DIMMs and ranks. The result is that a row can contain part of the cache lines from many different pages. In the page offlining mechanism, OS avoids using certain physical pages with potential underlying hardware fault. The faults are then masked and the UEs are avoided. The key here is to design a policy taking CE history as the input. The objective is to prevent more UEs with less memory capacity loss coming from page offlining. The traditional policy is based on CE rate. If we see a number of CEs in a page in the past 24 hours, the page is offline. This policy suffers from two weaknesses. First, errors are observation of the underlying memory faults. Some faults on a row or a column can impact many pages. Counting CEs in a page cannot reflect that. Here is a real example. There are 3 pages in a row. The first has more CEs. The second has less, while the third without CEs, encountering an UE. The second weakness is that not all the faults are prone to UEs. Another real example shows that though row 1 or pages in the row encounter more CEs, row 2 is the one with UE occurrence. This indicates that CE rate is not a good indicator of future UEs. In previous work, page offlining are evaluated using the metric of CE reduction, but not UE reduction in simulation. This is due to the lack of UE data with error addresses. An ideal evaluation is to use UE reduction as the metric. This is based on large amount of CE and UE data with error addresses. We propose the fault-aware prediction-guided method of page offlining. The first idea is based on the faults. Row faults are appropriate candidate for page offlining. This is because that a row is associated with at most 48 pages in the fully interleaved cases. In contrast, a column can map to a much large number of pages, making the offlining cost unaffordable. The second idea is based on UE prediction. We try to determine whether a faulty row is UE prone or not using ECC knowledge. In the new method, we first identify faulty rows, then check whether a faulty row is UE prone or not, and finally offline the pages in the faulty rows. To identify a faulty row, we look at the CEs in the row. If CEs in the past 24 hours scatter on a predefined number of locations spanning over a region with a predefined length, a row fault is identified. To determine whether a faulty row is UE prone, we count the number of risky CEs in a faulty row. If the number is over a threshold, then the row is UE prone. A risky CE is the one with its error bit pattern only partially correctable by ECC. In old days, any errors inside the DRAM chip is fully correctable by ECC, as is shown in this example. However, on contemporary Intel platforms, this is not true anymore. While ECC is highly confidential, Intel shares the fully correctable patterns under non-disclosure agreement with key customers and vendors. Here we show two examples of fully correctable patterns from a publicly available source. If the error bits are contained in the left half or the right half of the data pins, then the pattern is fully correctable. The same error cannot match with any of the fully correctable patterns. Therefore, it is regarded as a risky CE. We evaluate the new method on error data from ByteDance. The data is collected from around 10,000 SkyLake and Cascade Lake servers over 5 months. The servers run mixed workloads and are with DIMMs from a homogeneous manufacturer. There are a large number of CEs from more than 1,000 servers. There are close to 200 UEs. By varying the parameters, we show how the number of UEs avoided changes with respect to the memory capacity loss in both the traditional policy and the new policy. As we can see from the figure, the new policy avoids more UEs with the similar capacity loss. We also compare our new policy using the specific parameters to different baseline with the common parameters. Again, we see that comparing with the Windows or Linux policy, the new policy avoids times more UEs with the similar capacity loss. Comparing with those very aggressive policies, the new policy enjoys much less capacity loss, but still avoids significantly more UEs. More analysis and case studies can be found in our paper. To conclude, we have proposed a new fault-aware prediction-guided method for page offlining. The new method focuses on appropriate faults, that is, row faults. It also focuses on rows likely leading to UEs. Our empirical evaluation using large-scale error data shows that comparing with the baselines, the new method is able to avoid much more UEs with the similar cost of memory capacity loss. Here is the end of my talk. Any questions or comments are welcome. Thank you.